What materials do you use to build your rocket?
All the airframe this year is made of carbon, except from the tip. So the carbon tube, we did them in APCO, one of our sponsors. So during 1 week, a team went there every day and manufactured the carbon tube like they do in the industry. With the pre-preg carbon and an autoclave, so the big machine that goes that pressurize the tube and heat it to cure it. And we also did the fins in a similar with a similar technique. The carbon part of the nose cone. Couplers of the rocket are in aluminium, and they are we designed them on CAD. The workshop in EPFL manufactured them for us, or one of our sponsor Maxon. For the rockets, that's about it. So really this year it's all carbon. Last year it was a bit different with we had flax fiber for one of the tube that was done in one of the workshop in EPFL, and we had the aluminium tank for the hybrid engine that was designed by us but manufactured by one of our sponsors. As I mentioned, I think the engine is a COTS one, so we buy it. So we don't just have the casing and we fill it with the propellant. So not a lot of work on that, but we're working currently on a bi-liquid engine that is also just right there that we manufacture ourselves on the machine here.
What software do you use to design your rockets?
CAD. We chose to use SolidWorks. We have access to CATIA with the EPFL, but we just recent, and SolidWorks actually is a sponsor that gave us, I think, 200 or 100 license. So all members of the team can have a student license of SolidWorks, which is pretty cool because we can do thermal and fluid analysis with it as well. PCB Design, we use KiCad. So we try to unify the software on the team, just for everyone to use the same. So yeah, CAD, SolidWorks, PCB, KiCad. For the simulation, we use Open Rocket, but we have on RASIRO. All the previous year have developed and customized a simulator, like they done it from scratch. And every year it's getting better, and we just correlate the data from Open Rocket, from RASIRO, and from our own simulator just to have the final simulation. So yeah, that's developed software in the team. We will use a bit of MATLAB and Simulink for simulation, mainly on the engine side for last and next year.
And also concerning like simulation, like structure simulation or fluid simulation, we don't only use SolidWorks. We also use ANSYS, so Florent for fluid simulation, and we also use Abacus or also ANSYS sometimes. For structural simulation. We also mainly use Abacus for all composite simulation because that's how it was done in the past and we didn't change. Also license, also logistics that the software that we use to model the pumps that we're also working on, because our engine, like in our vision, the bi-liquid engine that we be able to propulse our rockets to space will have pumps. And so to develop that, we also use a license called Self-Turbo.
Yeah, so we'll talk about a bit the propulsion in the team. So last year we did the SRAD hybrid engine. So the hybrid engine was, oxidizer was nitrous oxide and the fuel was 3D printed ABS. So we 3D printed 5 small independent grains and glued them together with a 7 branch star pattern. That was last year, that worked very well. This year we buy the motor. I think it's a 1560 Cesaroni. Hopefully next year we want to use the bi-liquid engine developed currently by the project Hyperion. So we just assembled the first engine yesterday, so Demo A1, which is a ground test engine, and we want to develop a Demo A2 and maybe A3. So A2 is a flight version of this engine, which uses ethanol and nitrous oxide, and Demo A3 is the same but with liquid oxygen. But I think if we go for the main rocket, we will first time we will use nitrous oxide, and liquid oxygen is for later. And we also have the B class motor that currently doesn't exist, but are in development, that have 5 kilonewtons of thrust, regenerative cooling, and not immediately, but at the end, electric pumps. And I didn't mention them, but the A-class motor have 1 kilonewton thrust. For the production of the engine, the hybrid engine was mostly SRAD, except from the casing that was a Cesaroni one. And for the bi-liquid engine, actually we manufacture it all by ourselves. It's composed of, I think, 5 main parts, and we did them all on the lathe and mill here at the makerspace.
How did you develop your own PCB?
For the avionics, I think last 2 or 3 years, we have what we call the host board, which is a very adaptive board that have the memory and processing unit on it, with sockets to add some little modules. And on the modules, you could have GPS or telemetry or sensors. And the host board was like a credited project from 2 or 3 years ago. And this year, one of the team leader, the Avionics team leader, took the project, redo and modernize the host board. So he went from scratch with a new microcontroller. We did a new host board with the same principle, so with the computing unit and the memory on the board, and with 3 sockets per board to add some additional capacity. So I think we will have 2 boards in the rocket with 2 sensors. With every board will have a sensor additional board. One of them will have telemetry. The other one will have GPS, telemetry in LoRa and in Wi-Fi to send a video back from the rocket. We want to have a live feed from the rocket, potentially, from the side of the rocket and also from the parachute bay of the rocket, because at 9 kilometers, we can't really, it's hard to see the rocket, so we want to have a direct video link to see the deployment in real time. And how do we test our electronics? We want to fly it in a small scale rocket, so really take the same host board that will go in the main rocket, put them in small run, launch them in triple launches, and just see if it makes sense or not. Flight test is for electronics is really the best way and the way to go to test that. But we have also the payload that develop its own electronics. So the payload will have to use some cameras. So it'll have some electronics to record and save the feed from four different cameras, I think, but inside the rocket, looking at the experiment.
How do you transfer data from the rocket to a ground station?
Main telemetry with the data in LoRa, I think in 868 megahertz, and the secondary will be Wi-Fi. I don't remember exactly the frequency of the power, but like very powerful Wi-Fi to downlink the feed from cameras. I think we could have up to 4 cameras in the rocket looking at the parachute bay or the surroundings, so that's like a lot of data. And we have also SD card storage on board to gather after the flight. And for the ground station, we'll have they don't exist yet, but we have ginormous antennas, and it's not 100% sure it will be ready, but we want to have an automatic tracker, the LoRa and the Wi-Fi antenna on it that track the rocket automatically. That can also be moved manually in case there is a problem. So that's the plan for the tracker.
How do you make your launch rail?
This year we don't bring our launch rail, so we will use the EuRoC one. And as the rocket is COTS solid, we won't have any filling or things like that to do. And we don't plan to charge the rocket on rail because we have like a lot of capacity, and the launch window are pretty small for solid rockets, so it won't stay for hours and hours on the pad. So we don't have any worries on that. But last year, we manufactured our own rail and brought it to EuRoC, and you can see on the picture behind Alexandre the rocket, and this is actually our launch rail. So it's pretty massive. I think it's like 200 kilos with 3 legs and a 9 meters tower that we could extend to 12, but 9 was enough. With a complete ground station to fill the hybrid engine, the tank from the hybrid engine with nitrous oxide, and to ignite it. It wasn't mounted on anything, so we had to transport it pad with a van and assembled it. It took 1 or 2 hours really to assemble it. It's pretty long, but it was great to have our rail, to have a bit of liberty of how we wanted to do our launch. And actually, it was a collaboration with the Aerospace team, so they also used our rail at the competition last year.
How do you make your recovery system?
We use a system of 2 parachutes, so 1 drogue and 1 main. The 2 parachutes are actually done by the team, so it's SRAD. All of it is SRAD, also the manufacturing. And so we have the drogues that deploys at the apogee, and at 400 meters, we have the mains that deploys. If it was the case this year. And then, concerning how we made, I think, or how we designed them, it's mainly empirical method, I think. We just use one method and we do them. And then, so our spec is a bit one now of the highlight of the team, I think. So the first version was developed last year by a member. And basically, as I said before, he did not use any power techniques or cluster guides. The idea behind it is just to have an Income wires with just to have 2 springs that are.
I think you mentioned in the slide, the clamp band system. It's exactly that.
Exactly.
If you see what it's like.
And so so we have so two springs that are linked with nichrome wires, and then we pass a current through the nichrome wires that then melts, and the rocket is separated into. The ecosystem is tested one with an helicopter, thanks to one of our sponsors, and the parachute is also tested with drone flights, thanks to another one of our sponsors. So testing about ecosystem, we try really to test it a lot, even if we cannot test it in the exact condition of the flight, as we don't have a lot of launch opportunities.
Helicopter flight, like in 1 or 2 weeks, I think, and we will test the whole system. So it's like we had spare carbon tubes. Okay, I think they will use one of the spare carbon tube with the right mass, with the separation mechanism actually closed. They will launch it from the helicopter and hope it pen, and then check the main. Like we said with the in the past of the team, with a lot of problems with the main chute deployment, and last year it worked. So they used the same release system. So it's a 3-ring mechanism. I can't explain you exactly how it works, but it's the same thing used. Guys who jump with parachutes, and it's the same mechanism that deploy that. They use a similar concept because it was flight proven and it worked well. And we have a little additional feature. Historically, all the main chute of the team were red with a big Swiss cross, and this year is no exception. So we also have a red main chute with a Swiss cross, and we hope it happened in the Portuguese sky like last year.
What payload do you have?
I really like the payload from this year, so I'm happy to explain that. Last year's we had the CubeSat 3 units because the rocket was quite big. This year the rocket is 4 inches in diameter, so it's really small, and so we chose the CanSat format. So I think it's 66 millimeters in diameter and 115 in height, 1 unit, and we have like 3 units or 2.5, something like that. So it's like a long cylinder. And the science experiment is really cool. It's done by members of the team, but like the concept has been developed last year during Belarus 2, and this year they done the practical realization. It's always done like that for payload. We always do the payload from this year and like develop the one from next year. And it's a study about how the sloshing of liquids in rockets. So maybe you know that in commercial rockets, big one, Falcon 9, if you don't do anything, the propellant can slosh, so just bounce around the tanks during the flight, and this can break the equilibrium of the rocket and just make it spin and explode. So they have, I think, baffles in the inside, so just big metal grid inside to manage that, but it's pretty heavy. It's just dead mass. And what we try to do, it's, in the payload, we have 2 really small tanks with camera pointing at them to gather the data. One of them is just liquid with nothing, and the second one is liquid with foam on it, because we found and we think it's possible to really mitigate sloshing with a foam on top of the liquid that will be like a lot lighter than metal baffles inside the tanks. So that's the scientific experiment. We don't deploy it; it just sit in the nose cone of the rocket.